Okay, welcome to part 2 of your Kin 225 lecture for January 20th. This is one of the things I hate about face masks is I always tend to forget my face mask at home when I go out, and then you reach a place and you realize you have to go back home to get it. So in this part 2 of the lecture today, I'm going to talk about non-invasive determination of muscle fiber types. So in the previous part, I talked about determining muscle fiber types from your myosin ATPase activity or your myosin heavy chains. To do that, you'd have to take a muscle biopsy. So that's an invasive determination of muscle fiber types. The following methods are non-invasive ways to determine muscle fiber types. So the way this works is you can apply an electrical stimulus to a muscle. So let's say it's at time point here on the graph. After you apply that stimulus, you get a muscle contraction. So you see the muscle reaches a certain force output, and then the muscle relaxes. So we're going to try to differentiate between slow twitch or slow and fast muscles based on their contractile properties to an electrical stimulus. So this is called twitch contractile properties. So the question here is, which tracing is from a fiber with high myosin ATPase activity? So it would be your faster contracting fiber. The correct answer here would be muscle fiber A. When you deliver an electrical stimulus to this muscle fiber, it develops force very quickly and reaches its peak tension quickly. Whereas this one on the bottom, when you deliver an electrical stimulus, the force development is a lot more slower. So this one most likely has a lower amount of myosin ATPase activity compared to this one. So the one on top has the higher myosin ATPase activity because it has a faster time to peak tension. Now, which tracing is from a muscle fiber with a high sarcoplasmic reticulum ATPase activity? So recall the purpose of the sarcoplasmic reticulum ATPase is to break down ATP so that you can pump calcium back into the sarcoplasmic reticulum after muscle contraction. So that determines how fast your muscle relaxes after a contraction. So the correct answer here would again be muscle fiber A. Once it reaches its peak tension, it relaxes a lot faster than muscle sample B. So muscle sample B, you see, takes a lot longer of a time to come back down to baseline and to relax. So this one has the faster relaxation time. This muscle is able to pump calcium back into the sarcoplasmic reticulum after muscle contraction. Recall that the calcium has to come out of the sarcoplasmic reticulum, bind to troponin to cause contraction, and then it has to be removed and pumped back into the sarcoplasmic reticulum for relaxation to occur. So the top graph has the faster relaxation time. It would have the higher amount of sarcoplasmic reticulum ATPase. It can break down ATP faster to pump calcium back into the sarcoplasmic reticulum faster. So muscle fiber type classification can be based on your myosin heavy chain composition or your myosin ATPase activity, and that's used to call muscle fibers type 1, 2A, 2X, or 2B, going from slowest to fastest, or lowest myosin ATPase activity to highest. And this is a review. This is an invasive method to determine fiber type composition. You'd have to take a muscle biopsy to determine that those types of muscle fibers. The type of classification system I just talked about with the twitch properties. So this is in response to an electrical stimulus. In this case, the muscle fibers are called slow twitch, fast twitch A, fast twitch X, fast twitch B, again, going from slowest to fastest. So usually the slow twitch would correspond to type 1. The fast twitch A would correspond to type 2A. Fast twitch X would be your type 2X. And fast twitch B would correspond to your type 2B muscle fibers. Again, this is another twitch contractile property. So this refers to your muscle's susceptibility to fatigue. So in this case, we've taken a muscle and we've stimulated it repeatedly. So you can see the force develops and then it relaxes. You get development of force, relaxes. So this is repeated, a force tracing from repeated electrical stimuli. So you see the bottom muscle fiber, again, you get these repeated contractions, but in this case, you can see that the force drops off quite quickly, whereas the top one, the force is maintained. So the question here is, which one is a slow twitch fiber? The answer would be the fiber type, the one graphed with the letter A. So you have a smaller force production or smaller tension, but with repeated contractions, the tension is maintained better. So a slow twitch fiber is less fatigable than a fast twitch fiber. And a fast twitch fiber tends to have a great amount of fatigue. It has a high force output at the start, but then with repeated contractions, you get a rapid reduction in force. So it's very fatigable. So that's just another way that you can classify fiber types. You can call them fast, fatigue resistant, slow twitch, which have the least amount of fatigue, or you can call them fast fatigable. Those would correspond to your fast twitch B or fast twitch X muscle fibers. I'm going to get into the section here on fiber type conversion. So the first question here, the fiber types an individual possesses is determined strictly by genetics and cannot be changed. So the answer here would be false. So in a large part, your fiber type composition is determined by genetics, but your fiber types can actually change quite a bit with either increased use or increased disuse. I'm going to go over a few examples here. So the first one here, true or false, strength training with moderate to high repetitions leads to conversion of fast fibers to slow fibers. The answer here is true. So what happens with strength training is, you've got your three major fiber types here. You've got your 2X, your 2A, and your type 1. What happens with strength training is you get quite a large shift over time from the 2X to the 2A. Not much of a shift from 2A to type 1, but you'll see a reduction in your 2X muscle fibers because they're being converted to type 2A. So the question that a lot of people have is, if strength training leads to a shift of fibers from 2X to 2A, does your contraction speed actually decrease? And the answer to this is no, your contraction speed doesn't decrease. So one theory here is that you get this fast fiber type shift, but with strength training, your fast fiber types increase in size more than your slow fibers. And so despite having a bit of a shift to a slower fiber type composition, because the fast fibers occupy a larger area of the muscle following training, the actual percentage by area of the fast fibers doesn't really change that much. So I'm going to go over an example here. You've got, say, a muscle sample. Within the muscle sample, you have a whole bunch of muscle fibers. And let's say some of them are faster. So these are your faster fibers. And then say these are just your slower fibers. The white ones are slower. So with resistance training, you get a conversion from fast to slow. So in this case, you could have something like this. You get your slow fibers again. This one's converted to a slower fiber. But say these two have not been converted. So they're still fast fibers. So you can see what happens with strength training is you get preferential hypertrophy of these fast fibers. So despite the fact that some of them are shifting towards a slower fiber type, you still have a relatively large area of the muscle occupied by fast fibers because the remaining fast fibers have undergone substantial hypertrophy. Another finding here is despite the shift in fiber type from 2X to 2A, it appears that your myosin ATPase activity actually doesn't decrease because the ATPase activity associated with each myosin heavy chain, so type 2A, type 2X, actually increases. So again, despite the shift from 2X to 2A fiber types with strength training, you actually don't see that much of a reduction in speed of contraction with strength training. And that's pretty much it for today's lecture.